Hi everyone, thank you for joining. So in this video we're going to continue what we have done in the last video, the time dilation, but hopefully have a better understanding of it. We're going to do an example, right? If you remember in the previous video when we were doing the derivation of time dilation, we had this picture, two observers S and S dashed, and we used a mirror clock. And one thing to notice here is, of course, the clock is at rest in S dashed frame. Right, so clock is at rest at S dashed. Okay, and of course S dashed is moving with some velocity with respect to S. Right now, a few things to be said here. That the first of all, the frame S dashed is a special frame. So this frame of reference here is special. What makes it special? Well, it is the only inertial reference frame in which the clock is at rest. Clock is at rest. That's what makes S dashed special. Yeah. And the other thing to notice here is that when the experiment is going on here, that is the a photon is emitted and then it is detected. You have emission and detection there. One thing to realize that both these events are measured by the same clock. That's crucial, because this clock is at rest with respect to S dashed. So both events, that is emission of the photon and detection of the photon, are measured by the same clock. That's what sets the reference frame S dashed apart from every other reference frame, right? Because we will use this to define what a proper time is, right? And what is a proper time? Well, the proper time is the time interval between two events that occur at the same position, right? So I'll write it down, right? Now, what is quite crucial is that apart from S dashed, every other reference frame must be using two clocks. If you remember, we said in special theory of relativity, what you have is you have this space, and then it's made up of clocks, right? So every other observer, let's say S dash goes from there to there relative to an observer, every other observer will have to use two different clocks. S dash is the only one that uses the same clock, although spatially it's different locations, right? So, and I'll say a few more things about the time dilation. Now, how do we picture this time dilation? Well, you can think of it as stretching out of time. Stretching out of the time interval. Okay, this is how you could see it. So this is what time dilation is. But one needs to be very careful, because very often in physics textbooks you see it is described as the time dilation as being moving clocks run slow. Okay, this is not the best description of what is happening here. I think a better description is that the time interval between two ticks is the shortest in the reference frame in which the clock is at rest. I'll write that down. Okay, so the time interval between two ticks is the shortest in the reference frame in which the clock is at rest. Okay, so the time interval between the two ticks is longer. That means the clock runs slower when it is measured in any reference frame in which the clock is moving, right? Okay, so let's solve a question to understand this better. Okay, so we have a rocket here which is traveling from Sun to Saturn, and the speed is 0.9 c here, as you can see, right? And the distance is 1.43 times 10 to the 12 meters between Sun and Saturn. So the question we want to answer is this. Now, how long does the journey take as measured from Earth? Yeah. How long will it take? And similarly, how long would it take if it was to be measured by an astronaut on the rocket? So this is the question we want to answer, right? So if you pause the video here and then try it yourself first, then we can go over it together. Okay, so this is what we're looking at. If you look at the left-hand side, we're looking at the frame S, and that frame as it is observed from Earth, right? And this is observed from the rocket, right? Okay, so that's right. So let's do some calculations now based on the observation on the left from observed from the Earth. Relativity. Good thing about it, one might say, is that we still have this very basic formula: time is equal to distance over speed, or distance over velocity. So what have we got now? The distance was 1.43 times 10 to the 12 meters, divided by the speed 0.9 c, 0.9 times 10 to the 3 times 10 to the 8 meters per second, yeah? Which will give us, if you do carry out the calculations, you'll get something close to 5,300 seconds, yeah? Okay, so this is what we observed from Earth. All right. Now, what about the astronauts on the rocket? Well, clock would be moving with the astronauts. If you remember the definition of a proper time, so rocket will be using the same clock, although we are looking at spatially different points, same clock. So therefore, the time they are measuring will be proper time. Delta t is equal to delta t 1 minus v squared over c squared square rooted, right? So if you plug in the values, so what we're going to get is that that's equal to delta t over 1 minus, the speed was 0.9 c, well, c's will cancel, so we can just consider 0.9 squared, square rooted. So that implies delta tau is equal to delta t as observed from Earth, 1 minus 0.9 squared, square rooted, right? So delta tau will equal to, well, if you simply carry out this calculation, and we know from the first part that delta t is 5,300 seconds, you will get approximately 2,310 seconds, right? Okay, so yeah, as you can see, that it's almost a half of the value observed from Earth, isn't it? So this is what time dilation is. But one thing, of course, we need to bear in mind that it is a oversimplified situation. That is, the light would take some time to reach from the Sun and the Saturn to Earth. So the real values would be different because we have to take into account the fact that the light that we see there to there, right? So it will take some time to reach us, but we're just ignoring that, okay? Right. Okay, well, I hope you liked it. I hope you found it interesting. And in the next video, we will talk about some experimental, some evidence supporting Einstein's theory, special theory of relativity. This is all quite theoretical. Now we're going to see some solid evidence supporting Einstein's theory. Okay, thank you very much for joining, and I look forward to seeing you in my future videos. Thank you.